who is actually coming to us, zooming to us from almost the antipodal time zone. So we're very grateful for Ashok taking the time to do a late night lecture series. And well, Ashok, take us away.
Thank you very much. Let me try to share screen. Okay, can you see my screen?
Yes.
Okay, thank you. Okay, so first of all, I'd like to thank the organizers for inviting me to this school. Okay. It's a long time that I have been to TASI. Okay, I don't remember when was the last time I went there, okay, but thank you very much. And about the questions, I would request you to just, whenever you have questions, unmute yourself and ask, because I may not be able to keep track of either the chat or the raised hand during the screen sharing mode. So please ask questions whenever you feel like. Okay, so this is the title of my talk, String Theory and Black Holes. Okay. Oh, I should also say that the preliminary version of these lecture notes have already been uploaded on the web, okay, but I'll keep correcting them as I go along. Okay. So I have already said in those in the lecture plan that the topics that I'll cover in these, okay, are basically reviewed in this survey. Okay. This one doesn't have too much details. It's mainly a survey of the results, but all the original references you can find in this book. So let me then begin. So I'll start by writing down the formula for the black hole entropy, which I expect that most of you have seen in some form or the other. So and I'll be using units where I set h bar equal to 1 and c equal to 1, but g Newton I'll keep. So this is the Newton's constant. So this is what we normally call the Bekenstein-Hawking entropy. But of course, the concept of entropy came from thermodynamics, and which we know has its foundation in statistical mechanics. So in statistical mechanics, there is also a formula for entropy, okay, and that's log of omega. So what is omega? Omega is the number of microstates, okay, which are the number of quantum states corresponding to a given set of macroscopic charges. Which in the case of a black hole, you can think of this as mass, charge, angular momentum, etc. So these look quite different. Okay, this is purely geometric, where this is a counting problem. And the question that arises naturally is, can we give a similar interpretation or a statistical interpretation of the black hole entropy? Yeah, and this is the question that we'll try to address, and we'll see to what extent we can do this. So clearly, to do this, what we need to do is to count the number of states. And this is for given set of quantum numbers, for given mass, charge, etc. Now, in general, this is a hard problem, okay, because we don't really understand the black hole quantum mechanics very well. But what we'll see in these lectures is that string theory offers some hope. And this is what we'll discuss in these lectures. Okay, how string theory tries to address this problem. So here are the basic steps. So the first step is that we will try to identify a special class of black holes in a special class of string compactifications. Where the counting is possible. And we'll see that these correspond to extremal or BPS black holes. I'll explain these words as I go along. In a class of supersymmetric compactification. So once you can do that, we can calculate then A over 4Gn. And this has been chosen so that we can count the number of states. So we calculate A over 4Gn for these black holes. And compare with log omega. So let me, before I go on to discuss the details, let me just say that whenever this is possible, so here it's not just the black hole entropy formula that we saw, A over 4Gn, but there are also corrections, okay, that can be calculated systematically, and we'll see what these corrections are as we go on. And indeed, there are many examples. Of course, it's still a small fraction of the subset of the black holes that we have in string theory. In particular, this doesn't say anything about Schwarzschild black holes, for example. Nevertheless, okay, it's encouraging that at least whenever we can do this, we find perfect agreement with the black hole entropy. Okay, and that tests an internal consistency of string theory. Now, instead of trying to be very general, okay, and spread ourselves too thin, what we'll do is that we'll first focus on a particular example and discuss this in some detail. And then later we'll see, mention various generalizations. Okay, but the basic structure, the basic ingredients will be the same. Okay? So in particular, what we really want to discuss is how to do the counting of states, right? What goes behind this counting of states. And this particular example that we will deal with is a particular compactification of string theory. Okay, that's the heterotic string theory. Compactified on T6. So what is T6? T6 is nothing but product of 6 circles. So we have this identification that we call the compact coordinates are identified with period 2 pi. Okay, so this is for m equal to 4 to 9. And x mu, okay, which is the mu will be the non-compact coordinate index, are the non-compact coordinates. This is for mu running from 0 to 3. Okay, so this is the notation that I'll be using. Now, heterotic string theory may not be very familiar, so I'll not assume too much about heterotic string theory. What we really need at this stage is the supergravity that lies behind heterotic string theory, and more specifically, only the bosonic part of the supergravity. Okay, and that's what I'll try to describe in some detail. Are there questions so far? Okay, so let me then begin by describing the bosonic fields in 10 dimensions. So in 10 dimensions, that's where heterotic string theory is first defined. The bosonic fields they contain the metric, okay, the GMN, the two-form field BMN, a scalar, which is also called the dilaton, and a set of gauge fields. So this is metric, this is two-form, this is a scalar, which is dilaton, which is called the dilaton, and this is a set of gauge fields, which can be, there are two kinds of heterotic string theory, okay, either E8 cross E8 or SO32 gauge fields. M here is the coordinate that runs all the way from 0 to 9. So this will include both the compact and non-compact coordinates. Okay, but at this stage, we are just talking about 10-dimensional supergravity before compactification. So in the compactified theory, the fields GMN, BMN, and AMI, I'll explain what this index I is, can take any constant value. Okay, when I say can take any constant value, but that basically means that it's any constant value of these satisfies equations of motion. Okay. M, I have already said, this runs from 4 to 9. Okay. Now this index I, okay, runs over the Cartan generators of the group. So I runs from 1 to 16. Okay. You would perhaps note that both E8 cross E8 as well as SO32 has rank 6. Okay, so its Cartan subalgebra is 16-dimensional. Thought it has a 16-dimensional Cartan subalgebra. Okay. Now, why do you have to take it in the Cartan subalgebra? And the reason is that we want the field strength to be 0 in order that it satisfies the equations of motion. And for that, we need that if ABC, AMA, AM, ANB should be 0, okay, for all M and N. Because if the field strength is non-zero, it will contribute to the energy momentum tensor, and that will make the metric curved. Okay, you cannot get the solution with a flat metric. So these class of solutions require that the field strength is 0, and that's why you have to take this to in the Cartan subalgebra. And this has the effect that this breaks the gauge group. Typically, as long as these are all non-zero, okay, this breaks the gauge group. To U1 to the 16. Okay, because this is like a vacuum expression of the adjoint scalar fields. Okay, so it breaks it to U1 to the 16. Okay. Now these have to be constant if you are going to look for a solution, okay, which is or the class of vacuum solutions. Okay. But of course, from the point of view of 3+1 dimensional theory, these act as scalar fields. Okay, so they can actually vary as a function of x, and then they are no longer automatically solutions to equations of motion. They have to satisfy appropriate equation, differential equations for them to be solutions to the equations of motion.
Question?
Yes, go ahead, please.
I understand why there will be solutions for which these fields are all constant, but it sounded like you just said that they have to be constant. There's some condition that requires the fields on the torus to be constant. Can you explain that?
No, I didn't say that they have to be constant, but in general, what will happen is that if they're not constants, okay, then it will produce energy momentum tensor, non-zero energy momentum tensor. Okay, for example, suppose if mu nu was, if mn was non-zero, that will produce non-zero energy momentum tensor, which will act as a source of the Einstein's equation. And in general, it will produce a curved metric. You don't get a flat metric anymore.
Thank you.
But in special cases, you can try to see if one can get an appropriate solution. And indeed, there are solutions known where there are non-constant configurations in the internal space. But typically, those are not flat space solutions. Here, what you are looking for is a solution where the 3-dimensional or the 3+1 dimensional space is flat, Minkowski. And there, the class of solutions correspond to these being constants on the torus.
Thanks.
Excuse me, can I ask a follow-up question about that?
Yes, go ahead, please.
Why do you necessarily need a flat space metric?
No, we don't necessarily need a flat space metric. It's that it's easier for me. I mean, the class of black hole for which we'll be doing the counting, for those we need the flat space.
Okay, thank you very much.
Yeah, but certainly it's not that. So these are one class of compactifications of strength. Let me put it this way. Certainly, these are not the only class of compactifications.
Thank you.
Thank you. Okay, so then let's count the number of scalar fields that we get from here. So GMN, BMN, and AMI. These act as scalar fields in 3+1 dimension. So let's first do the counting. Okay, so this is a 6x6 symmetric matrix, so that's 21. This is 6x6 antisymmetric matrix 15. And here M runs from 1 to 6 and I runs from 1 to 16. So that's 6 times 16, so that's 96. So if you add this up, okay, you get 132 scalar fields. It turns out that there is a convenient way to represent these 132 scalar fields. And that is that we can encode this into a 28 by 28 matrix M, satisfying the following constraints. First of all, M is symmetric and ML transpose equal to L, where L is a given matrix. So IN is n by n identity matrix. So these are 6 by 6 identity matrix. So this is a 6 by 6 block. And this is a 16 by 16 block. So that makes it 6 plus 6, 12 plus 16, 28. Now, why we want to do this? Okay, that is a long story. I'll not describe this. Okay, but we do have explicit expressions for M in terms of these. Okay, which is somewhat complicated, and so I have not written it down. But one thing you can do as an exercise is to check that the number of independent components of a matrix that satisfies these constraints is indeed 132. Okay, so these.
Sorry, can I ask a question?
Yes, go ahead, please.
Shouldn't we subtract some degrees of freedom coming from the gauge transformations from all of these fields? So shouldn't we get less than 132?
Yeah, okay. So the point is that you don't have any discrete gauge transformations, any continuous gauge transformations anymore. But you have discrete gauge transformations. Because see, there is periodicity, right? Suppose you want to have constant G. Okay? Normally you would say constant G can be made into delta Mn. Okay? But that requires gauge transformation, the general coordinate transformation parameter that grows linearly as a function of coordinates. But once you have periodicity, okay, a gauge transformation parameter that grows linearly is not a allowed gauge transformation parameter. So there is no continuous gauge transformation anymore, but there are certainly discrete gauge transformations, which you have to quotient by, but that doesn't reduce the number of scalars, number of scalar fields.
Okay, so it's the putting on a T6 that breaks these continuous gauge transformations.
Exactly, yeah.
Okay, thank you.
So this, for example, is what we call Wilson lines, right? Just the constant value of gauge field along a circle that you cannot remove by gauge transformation. Okay, are there other questions? Okay, so this gives you 132 scalars. Now we also have the phi, okay, which is of course there. Scalar in 10 dimensions goes over to a scalar in 4 dimensions. But we also have this field B mu nu, okay, which is a 2 form in 3 plus 1D. This can be dualized to a scalar, okay, by simply saying that dB, which is a 3 form, we can write as a Hodge dual of d chi. Okay, this is the Hodge dual. And chi is a scalar field. Okay, so a 2 form in 3 plus 1 dimension is dual to a scalar. Okay, so that's what we'll do. Okay. And then it's useful to combine this chi and phi into a complex scalar field. Okay. So tau is chi plus I e to the minus 2 phi. Okay. This becomes a complex scalar. And indeed, the dilaton, if you may be familiar with the fact that e to the phi actually measures the string coupling. So this, the expectation value of this is I over G string square. Okay, that's I over string coupling square. But I'll discuss this in a few minutes.
Can I ask a question?
Yes, go ahead, please.
What are you like? What property of P mu nu are you using to express it in terms of a scalar, or is it just that it's anti-symmetric, or?
Exactly, it's a 2 form, right? And it satisfies a standard differential equation that so the its box B mu nu equal to 0 in an appropriate gauge, the differential equation that it satisfies is box B mu nu equal to 0. Okay, or another way of maybe I should have said something else, that this has a intrinsic gauge invariance, okay, which is B goes to B plus D lambda. Okay, this is a gauge invariance. Okay. So using this, you can argue that the gauge invariant field strength is H, which is dB. Okay. And that, so that this is the full gauge invariant content of this two-form field. Okay. And that you can write, because it's a three-form, okay, you can always write it as a dual of a one form, and then the differential equation that H satisfies, okay, basically tells us that the chi is, the differential equation on chi is like a massless scalar field. So it's essentially the equations of motion for B, okay, is equivalent to, so all the solutions to the equations of motion for B is equivalent to the solutions of equations of motion to a massless scalar. That's what we are using here.
Thanks. Yes. Thanks.
Can I ask you a question?
Yes, go ahead, please.
Is there any a priori reason why you're taking e to the minus 2 phi? I'm assuming you want it to belong to the upper half plane, but is there a reason for doing that?
Yeah, the reason for doing that is because this is a natural variable, and we'll discuss the various symmetry transformations. So at this stage, of course, you could have asked this about M also, right? Why are you going to combine all of these into this matrix M? Right? When I discuss the symmetries, you will see that the symmetry transformations act in a somewhat natural way on these variables. Okay, and that's the reason we take these particular.
You miss certain hidden symmetries if you don't use this formalism.
No, you don't miss hidden symmetries, because of course a symmetry, once it's there, you can write it in terms of any variables that you like, right?
Right.
Changing field variables.
Be manifest.
Yeah, it's just that it's manifest in these variables.
Okay, thank you.
Are you going to be assuming that there are no cross terms between the Minkowski factors and the compact factors?
Yes. So here it's just normal onward compactification. Okay, it's a product space.
Thanks.
Yeah, but typically what happens is once you introduce fluxes, then there is warping between the once you take, for example, this question which came up, that if you take these GMNs and BMNs not constants in the torus, but say dependent on the torus coordinates, then there are solutions which are warped. Okay, but here we are certainly assuming that it's just a product space. So these fields, M tau, these are known as moduli fields. Because any constant value of these fields gives a solution. Okay, and that it gives a solution that is Minkowski from the 3+1 dimensional viewpoint. So it can take any value. Okay. And these basically describe inequivalent vacuum of the theory. So this finishes the discussion of the massless scalars. Now let's look at the massless gauge fields. So first of all, you have the gauge fields in the Cartan generator. That's the 16 U1s come from there. Remember that we had to begin with H cross C8 and SO32, but once you gave vacuum expectation value to the internal components of these Cartan generators, typically all the off-diagonal gauge fields become massive, okay, because you are giving it a vacuum expectation value to the adjoint scalar. So the massless gauge fields are only these in after compactification. And then we have GM mu and BM mu. Okay. So this gives you 16. Okay. This gives you 6 gauge fields because M can take 6 values, and this gives you 6 gauge fields. Okay. So you get altogether 28 gauge fields. And finally, the massless fields also include the metric in 3+1 dimension, which is G mu. Okay. And you have known action for this theory. Okay. So I'll not write down the action, but let me just say that the action of these massless fields, at least in the two derivative approximation, is known. Okay, so you can write down the action, you can write down equations of motion, you can construct black hole solutions. Anything that you do in a theory of gravity, you can do in this case.
I'm a little confused by those GM mu, BM mu terms, because I thought you just said there would be no cross terms in the metric.
Yeah, so these are 0 in the vacuum, but these are fields in the theory in 3+1 dimensions.
Mhm.
So when you construct a black hole solution, for example, then these can be non-zero. So in the vacuum solution, right, the 3+1 dimension, when the 3+1 dimensional space is space-time is Minkowski, then there is no cross term. Is that point clear?
Yes, thank you.
Any other question? So now let's look at a generic state of this theory.
Excuse me, I have another question. If you can clarify a bit what you mean by saying that the fields m tau can take any value and they are inequivalent vacuum of the theory. That this last statement.
Yeah, okay. So let's take, suppose you take different values of m, right? So what do different values of m correspond to? Different values of m correspond to giving different values to GMN and BMN. Okay, and these A's. So these are solutions of the theory. And the solution is, as far as the 3+1 dimensional theory is concerned, it's pure Minkowski. So in that sense, it's a vacuum solution. Okay, because we'll define solution toward the space time, the 3+1 dimensional space Minkowski as a vacuum. So these will be vacuum solution in that sense. Is this point clear?
Yes.
Okay. Yeah. In other words, okay, let me go back one step. Okay. These are the metric on the torus, right, on T6. So different GMN, right? What does it mean? That means that a T6 has different shape, right, or different size and shape, and that we'll call inequivalent vacuum. Okay, different size of the compact dimension corresponds to different vacuum of the theory. Is this point clear?
Yes, thank you.
Okay, so in this theory, if you take a generic state, including a black hole, will carry 28 electric charges and 28 magnetic charges. Okay, so a charge vector then will denote by QP. Because there are 28 gauge fields, so each of these gauge fields have their own electric charge definition. So we'll have 20 electric charges, and we are also allowing magnetic charges. Okay, so a generic state will have both electric and magnetic charges.
So it's not just U1 to the 16 then. You said that the gauge symmetry is broken to U1 to the 16, but you have 28 charges, so it's not just
so
U1
U1 to the 16 came from the original gauge symmetry, right? In 10 dimensions, we had 8 cross 8 and S32. Okay, that gave U1 to the 16. But besides this, you have this GMU and BMU.
Yes,
Those also appear as gauge fields in lower dimension. Okay, so that's why you have 28 electric charges. So some of these electric charges will actually represent momentum in the internal dimension or string winding in the internal dimension. Okay, those will be sources of GMU and BMU. Now, in this theory, Q is quantized, okay, as in most theories. So Q is quantized. It's not hard to understand why it is quantized. For example, the GMU charge, right? That's the momentum along the internal dimensions, and that of course is quantized, right? Because once you have a circle, the momentum along a circle is quantized. The charge corresponding to BMU, okay, are the winding charges. A string can wind multiple times. Those are the ones that generate sources of the BMU, okay, and that's also quantized in integers. So Q is quantized. And of course, the gauge charges are quantized. The 8 cross 8 gauge theory has quantized charges. So the fact that this is quantized can be stated formally by saying that Q takes value on a 28-dimensional lattice which I'll denote by lambda. And then immediately Dirac quantization rule says that P takes value on the dual lattice. Now, it's a result here that, which I'll not prove, but I'll just state, that in this particular theory, okay, lambda is self-dual. Okay, which means the dual lattice is the same as the original lattice. And that means that P also takes value on lambda. This will be important in a few minutes. Okay, so Q and P, in this theory, Q and P both take value on the same lattice. Okay. But I should just say that this is not a generic feature of compactifications of this kind. This is somewhat special, that Q and P takes value on the same lattice.
Sorry, so how would it be that they're not self-dual? Do you just mean that the dimension wouldn't be the same, or something about the spacing? Or
no, dimension will be the same, right? But it could be, for example, that the Q is half integer and P is even.
Okay.
Okay, so then we'll say that they are not the same lattice.
Got it.
Okay, but it just so happens that in this case they are on the same lattice.
Thank you.
Okay, there's one more thing which is not going to be very important for this lecture, but let me just say it anyway. That in 10 dimensions, 8 cross 8 and S32 heterotic string theories are distinct string theories. Okay? But once you compactify on a circle, okay, or a number of circles, then you can show that the two theories become identical. Okay? They are equivalent. Okay? Which basically means that if you look at the space of M and tau on the heterotic on the 8 cross 8 theory, and the space of M and tau in the S32 theory, okay, then for every value of m in one theory, there is a corresponding value of m prime in the dual in the other theory, where you can show that two theories are the same. Okay, so in that sense, the two theories become identical once you compactify on a circle. So because of this, it doesn't really have to, we don't really have to commit ourselves as to whether we are dealing with 8 cross 8 heterotic or S-ordered heterotic, because they are the same theories. Okay, now let me discuss the symmetries of the theory.
So can I ask one more question?
Yes, go ahead.
Does the action not include the fluctuations of the scalars, like which are included in M and tau?
Yes, indeed, they do.
It includes the fluctuations of these scalars as well, right?
Yeah, yeah. So the action, when I said that this is known, right, it involves, of course, derivative of the scalars, right? There are kinetic terms for the scalars, gauge fields, and so on.
So there is some background, but then there is kinetic term as well for
Exactly.
M and tau.
That's it.
Okay.
So the background corresponds to these being constant, and then there are fluctuations.
Yes. Okay.
So the background gives a vacuum solution, then you study fluctuations of these in the background. Right. So when you look for various solutions, for example, black hole solutions, then these are not going to remain constants. Okay? Typically, these will vary as a function of space. And okay, if it's a static solution, it will vary as a function of radial coordinate, for example.
Okay. Thanks.
Okay, so now let me discuss the symmetries. So the first important symmetry will be T-duality. Okay. I'm not discussing the gauge symmetries here, okay, because those are of course there. So T-duality takes the following form. Well, unfortunately, I'm using this omega. Maybe I make it small omega, because omega I had introduced as a counting number of states. I hope I'll stick to it. Okay, so this is the way the M transforms. I'll explain what omega is. Okay. Instead of giving the transformation of the gauge fields, I'm going to give the transformation of the charges, but it's basically the same thing. So this omega is a 28 by 28 matrix. Satisfying omega L omega transpose equal to L. I'll write down the expression for L if in case you have forgotten. Okay. But let me write the other condition, omega lambda equal to lambda. Okay. So L was this matrix, okay, 28 by 28 matrix, which is this. So I16. Okay. So this is a 28 by 28 matrix satisfying this. So this is what is called the SO622 group. Okay, because if you diagonalize this, you will see that this has six diagonal elements with positive eigenvalue, or eigenvalue +1, and the rest eigenvalue -1. Okay, this is O622 matrix. Okay. But this is important. This says that omega preserves the lattice. Okay, so what this actually means, okay, that omega acting on an element of lambda, okay, that means a lattice vector gives another element of lambda. It could be the same element, typically another element. Okay, that's what it means by omega acting on lambda is lambda. Okay. And of course, you can see this is important because otherwise, if you take a particular Q which is on the lattice and if you apply omega inverse, okay, you better get something that satisfies the same quantization law, right? That means it should be part of the same lattice vector. Okay, and that's what this one this ensures. Okay. So this is a discrete group. Okay, so because of this condition, this is a discrete but non-compact group. Okay, this is sometimes referred to as SO622 Z. So that is T-duality group. Okay. This includes, for example, if you are familiar with some aspect of string theory, there is a R goes to 1 over R duality. Okay, you can take a radius and invert it. Okay, that is included in this. Okay. And the other symmetries that are included are the standard diffeomorphisms. Okay, that we discussed this earlier, that if you take a torus, right, the continuous gauge transformations are gone. Okay. But of course, you can relabel the coordinates of the torus, for example. You can call 1, 2, and 2, 1. Okay. Or 1, 2, and 2 minus 1. So that's a symmetry that is present. Okay, that's part of this T-duality.
Sorry, maybe my screen's cut off, but at the top, did you write tau goes to tau inverse?
No, tau goes to tau.
Okay.
Tau doesn't transform under
Okay.
this. Yeah. Okay, so because of this property, we'll define an inner product. Okay, this suggests that we define inner product. Alpha dot beta, which is alpha transpose L beta. Okay. So, for example, Q square in this notation will be Q transpose LQ. P square will be P transpose LP. Q dot P will be Q transpose LP, and so on. These are all invariant under T-duality. Okay, you can easily convince yourself that this one, because of the property of omega, it's invariant under T-duality. Okay. But of course, there are also other invariants you can consider. For example, Q transpose MQ is also invariant. Q transpose MP is invariant, and so on. The second important symmetry is S duality. So under this, M goes to M, tau goes to A tau plus B over C tau plus D, and QP goes to A, B, C, D, acting on QP. Okay. Where A, B, C, D are integers, and they satisfy AD minus BC equal to 1. Okay. So this is also a discrete group of symmetries. Okay. But this is called S duality, and indeed this includes, in particular, tau goes to minus 1 over tau. Okay, you can see you have to choose B and these quantities properly. B equal to 1, C equal to minus 1, and A and D 0 will do the job. Okay. And this is what is called a strong weak coupling duality. Because if you remember tau, okay, there is a scalar field that you got by dualizing the B mu, but then you had this I to the minus 2 phi, whose expectation value is I over GS square. Okay. So for example, if this chi was 0, then tau goes to minus 1 over tau, will send GS to 1 over GS. So it takes you from strong coupling to weak coupling and vice versa. Okay, that's why this is called a strong weak coupling duality. But this also one can show is a symmetry of the theory. Okay, this is a non-perturbative symmetry. Okay, when I say one can show, okay, it's conjectural, but there is plenty of evidence that this is a genuine symmetry of the theory. The third important symmetry is, of course, supersymmetry. Okay. So this theory has what is called n equal to 4 supersymmetry in D equal to 4. Okay. That basically corresponds to 16 unbroken supercharges. So heterotic string theory in D equal to 10 had n equal to 1 supersymmetry that also had 16 unbroken supercharges. And torus compactification doesn't break any of the supersymmetries. Okay, so it have 16 unbroken supercharges. Okay. And so the massless fields that we had seen in the massless fields, they describe n equal to 4 supergravity coupled to n equal to 4 gauge theory with gauge group U1 to the 22. Now you wonder where does this 22 come from? Okay. So basically the point is that we have 28 gauge fields, okay, but 6 of them are actually part of supergravity. Okay, if you just wanted to write down n equal to 4 supergravity in 3+1 dimension, okay, that has a metric, okay, but that also has 6 gauge U1 gauge fields. Okay. So that's part of supergravity, and then the 22 other gauge fields come from matter. Okay, they represent what is called the matter multiplet. Okay, that's why the gauge group is 1 to the 22.
Can I ask a question?
Yes, go ahead, please.
So what about the massive states? Or the
Yeah,
massive
so
fields?
massive states you are not including right now, and they will not be important for what we are going to do. But there are certainly infinite number of massive states in this theory. Because you are looking for black hole solution which are constructed basically out of the massless states, right? We imagine that you have already integrated out all the massive states and written down an effective field theory in 3+1 dimension. Is that clear?
Yes, thank you.
Should we think of the T duality and S duality as a global symmetry or a gauge symmetry of the effective field?
So these are actually gauge symmetries, okay, because what one can show that you actually have to identify fields under that related by these transformations. So they are actually discrete gauge symmetries of the theory.
Thank you.
One way to motivate this is that this includes, in particular, the diffeomorphisms of the torus, right? That exchanging the coordinates, for example, the names of the coordinates. That certainly is a gauge symmetry because that's part of the diffeomorphism that we had to begin with. But the whole symmetric group, you can actually, you should think of this as a gauge symmetry. Okay, so now let me come to black holes. So this theory has black hole solutions. And these are labeled by charge vectors. The 28-dimensional charge vectors, QP. Mass shall call M, and angular momentum. Okay, let me call this J tilde because we will see a different J later on. Okay, just to not confuse this. Okay. But we'll be really considering the non-rotating solutions. So we'll consider J tilde equal to 0 solution. Okay. Now I should say, when I said that this theory has black hole solutions, these actually have been explicitly constructed by solving the equations of motion, okay, at the level of the two derivative action. So these are generalizations of the Rice and Nordstrom solution. And like the Rice and Nordstrom solution, it has extremal limit. Okay. And this extremal limit corresponds to fix the charges. Okay, angular momentum, of course, is 0. Okay. And then you start reducing the mass, okay, till the two horizons coincide. Okay, typically a charged black hole has both outer and inner horizon, and that's true in this case as well. Okay. And you start reducing the mass for a given set of charges, and you go to the limit where the two horizons coincide, and that's the extremal limit. Okay. So m goes to m extremal from above. And at this stage, the inner and outer horizons approach each other. Okay. So this, in a sense, is a bound on the black hole mass. Okay. Because if we want non-singular black hole, well, by non-singular, I mean where the singularity is hidden behind event horizon. That requires that m should be larger or equal to m extremal. This is the bound. Now, a peculiar property, well, perhaps not so peculiar by now, okay, a property of these extremal black holes is the following. Extremal black hole, okay, which corresponds to m equal to m extremal. These are invariant one quarter of the supersymmetries if the charge vector is such that q square is positive and p square is positive. Okay, otherwise the extremal black holes are not supersymmetric. So we'll be focusing on this case. Okay. So when you say that it's invariant under one quarter of the supersymmetries, what precisely one means is the following. Okay. So remember that we have 16 supercharges, okay, 16 unbroken supersymmetries in this theory. Okay. So one quarter of 16 is 4. Okay. So it has 4 killing spinors. Okay, so under these 4 supersymmetric transformations, the black hole solution doesn't change. Okay. So these are called 1/4 BPS black holes. Okay, and the mass is called a BPS mass. Okay. So that means that for this class of black holes, for q square positive, p square positive, okay, as you reduce m, okay, then as m goes to m BPS, the black hole becomes extremal. And if we reduce m below m BPS, okay, then you don't have the singularity hidden behind the horizon anymore.
Can I ask?
Yes.
Are there also half BPS black holes in this theory?
Yeah. So there are half BPS states, but those have singular horizon. Okay. So they are at the level of supergravity, they are singular solutions. But there have been arguments that once you include higher derivative corrections in the theory, then they become non-singular. But we will not consider those in this lecture. Okay, because those are at the level of supergravity, they are actually singular solutions.
Great, thanks.
And those also require very specific condition on Q and P, okay, which is that Q should be parallel to P. Okay, so let me say half BPS, not black hole, let's call this half BPS states have Q and P parallel. Okay, so typically when you look at the formula for MBPS, this is a complicated formula for QP, okay, the charges, but this also depends on M and tau. Okay, so these are values at infinity. Okay, so M and tau, as I said, they vary, of course, with the radial coordinate. Okay, so when I said there are functions of M and tau, these are the values at infinity, because that's what controls the vacuum. Okay, but at the center of the black hole, they take different values. So it's in general a complicated function. This is known but complicated.
Can I ask a question?
Yes, go ahead, please.
So can these, actually 2 questions. Are these black holes considered stationary?
Yes, they are in fact static. Yes.
Okay.
They're not rotating.
Fair. And is there like, can you restrict like the possible stationary, I guess, static black holes that could be written down?
That could be.
For example, in just vanilla GR, there are only so many different stationary solutions you can write down.
Yeah. So certainly that's the case here, right? That once you fix the charge QP, mass and angular momentum, the solution is fixed.
I see.
And then we are considering the static solution where J tilde is set equal to 0. So there is no ambiguity in the solution. So the solution is fixed, and you calculate its various properties.
I see. Thank you.
Okay. What is surprising at this stage, okay, is the formula for the entropy. Okay, so I'll write it again, but let me write it here. This is independent of M and tau. And this is going to be important for us. So I'll write it again in the next page, maybe before I discuss this in some detail. So S is pi square root of Q square P square minus Q dot P square. So no M and tau dependence.
Is this the extremal entropy?
Yes, indeed. So this is for extremal, for BPS.
Oh, sorry. Go ahead.
I was just going to ask, how did you arrive at that expression?
Oh, just by calculating the area of the bag, because as I said, the solution is known, right?
Okay, so
just calculate the area and divide by 4 times the Newton's constant. That's what you get.
And that's what you did. Okay.
Yeah, exactly. So this is calculated by A over 4GN. Yes.
So the M you refer to here, that's not the mass, that's that matrix that you defined before, right?
Yeah, exactly.
Okay.
So small m is the mass. Okay, so m is MBPS. So that formula is very complicated, which I didn't give. Okay, here I said that it's a complicated function of the moduli as well as the charges. But the entropy has a simple formula, which doesn't depend on the moduli. Is that okay?
Yeah, thank you.
One question, why do we think that the black hole entropy formula that we got from classical thermodynamics should apply for BPS states?
okay, I mean, you can think of this as a limit. Okay. And the other point is that it's true that you cannot really do thermodynamics because the temperature for these black holes goes to 0. Okay. But you can do something like thermodynamics because you can still ask about its variation with respect to charges, okay, and relate it to chemical potential. So there are some aspects of thermodynamic relations which these black holes still satisfy. Okay. How the entropy varies with charge, that is related to the chemical potential and so on. But otherwise, you can just think of this as a limit of a regular black hole.
Makes sense. Thank you.
Question. Is it possible to have zero entropy black holes that have non-zero Q and P?
Yes, these half BPS ones are like zero entropy. That was, but a zero, you can see the zero entropy black hole means that the area is vanishing, right?
Right.
And if the area
I'm just saying
vanishes,
from this
the
above
event
formula.
horizon is singular.
Right. Okay.
So the half BPS black holes are like that.
I see.
Another
But again,
question?
as I said, there are general arguments that higher derivative corrections will make the entropy non-zero. Okay, but it doesn't happen at the level of two derivative standard supergravity. Any other question?
Can I ask one more question?
Yes, go ahead.
Is that these BPS solutions also to be intended as zero temperature black holes? And so is this entropy a 0 point entropy?
Yes, you can think of this as a 0 point entropy. Because these do have different temperature. Okay, so these are T equal to 0.
Can I ask a question?
Yes, go ahead, please.
Can you also have zero mass black holes in this context?
Well, at some limit of this half BPS states, zero mass state. Okay, but those actually correspond to also Q and P is going to 0.
Okay.
Yeah, but I think they are really singular objects, right? So one shouldn't think of these as black holes. I mean, what we'll call black holes are the big objects, right? Where the curvature is weak at the horizon and you can trust what you are doing.
Okay.
Okay, so our goal will be to reproduce this formula from counting. SBH, but as I said, there will be corrections as log omega. Now, as we have been emphasizing that this is difficult to count in general, okay. But we'll argue now that for BPS black holes, there is a way out.
Sorry, can I ask one question before that?
Yes, please.
So you had some action, and the claim is that there are solutions to the equations of motion which look like black holes. But is it clear that for given charge and for given charges that these black holes are the only solutions? You could have other solutions of the equation of motion with the same charge, but which are not black holes.
Yeah, okay. I'm not completely sure about the status, but there certainly has been a lot of work proving absence of solutions. I don't know how far the no-go theorem goes, but I think for these class of solution theories, I think the no-go theorem is valid because this is like standard Einstein theory coupled to scalar fields and gauge fields.
Mm-hmm.
So I think for these class of black holes, I mean, there's a no-go theorem that these are the unique solutions.
But I mean, could there be I'm just thinking like naively, could there be a star, like not a black hole, but like a solution which is not a black hole, but
yeah, there can be a star, but I think the BPS limit, they will become the black hole solution. Because you can get these solutions, in fact, also not by solving Einstein's equation, but by simply requiring that it has supersymmetry. Because it admits scaling speeders.
Yes.
So that's another way of getting this solution. So if you want supersymmetry, then that basically leads to these.
I see.
So
Okay.
otherwise, you are right, and you can get star-like solution.
Okay. Thanks.
Ashok, you have 5 minutes just already.
Yes, yes. Okay. Okay. I'll just say something about the index and then I'll stop. Okay. So we'll now introduce the notion of index. Okay. And the particular index that we'll be using is what is called B6. Then number 6 will become significant soon. Okay. So this is a definition. B6 is 1 over, okay, it is a function of Q and P. That's 1 over 6 factorial trace of -1 to the 2h to the 6 QP. Okay. So this trace means, so let me explain what trace is. Trace is taken over all states in the center of mass frame. So at rest, you can say. Okay, but it could include multi-particle states as well, with given charge QP. Okay. H is the Z component of angular momentum. And that's it. That's what defines this B6. The important result, okay, that I'll prove next time, is that B6 gets contribution only from BPS states. Okay, in particular, quarter BPS state contribute. Okay. Non-BPS state does not contribute. Even if M equal to MBPS accidentally. Now, what I mean by accidentally is the following: that imagine that at a generic point in the moduli space, the state is non-BPS. But as you move in the moduli space, at some point, the mass of the state may just happen to become equal to MBPS. Okay. Then it will not contribute to B6. So because of this property, one can argue that as a consequence is that B6 QP does not change as M and tau vary. Okay. So let me remind you again, okay, that B6 gets contribution only from BPS states. Okay. And so as you change M and tau, okay, the spectrum, okay, this is, you can see this is more or less like Witten index, right? -1 to the 2h would have been just Witten index, because this counts so that the state is fermionic or bosonic, the 2h being integers or half integers. Okay. This is extra. I'll explain next time why this is needed. Okay. But otherwise, it's like the Witten index. Okay. And just as Witten index doesn't change continuously, okay, as you change parameters, okay, one can see that the B6 will not change continuously as you vary M and tau. Okay. There are exceptions to this, which I'll discuss as we go along. Okay. But this is generically true. Okay. So, okay, this I'll try to explain next time in more detail, but let me just say that, so the upshot to be discussed next time is that we'll argue that we can compare B6 with exponential of the Bekenstein-Hawking entropy. Okay. This can be counted easily. Well, no, maybe not so easily, but at least this can be counted. And this can be computed. I have already given you the formula. And then you can compare the two. But I think this I'll try to discuss next time in some more detail. So I think my time is up, so I'll stop now.
Thank you very much. So I will invite, instead of having the questions recorded here, I would invite everyone to move to the Gather Town and then keep asking questions. So the next lecture will be in half an hour. So let's all then
Okay.
keep
So
asking.
how do I move to Gather? I mean, is there a
So there's a link that you go to by email to Gather Town. Did you try
I see,
Gather?
okay. I've not tried. Yeah. This, okay, I'll try it. I'll do it. Yeah. I think it's also available in Slack. In